now to talk to you about good cloud AutoML.
Thank you very much. I've enjoyed all these presentations so far. They're all amazing. I was aghast listening to some of the numbers coming out of NVIDIA there. It's pretty amazing. First, I want to apologize. I have to give this talk in American English, not British English. So hopefully you'll all be able to understand me okay. My name is Kevin Nelson. I'm in developer relations at Google. I focus a lot on storage and then what you do with bits once they're up in the cloud. That kind of flows over into big data analytics and now machine learning. Over the last 3 or 4 months, that has been almost exclusively in the machine learning area because there's just such demand for the topic. I like to think of machine learning as really 2 different things. The old way of programming is you come up with a set of procedures, heuristics, you figure out ways you want to do something. In machine learning, we're addressing problems that either can't be done at scale or can't be done at all. Can't be done at scale example would be there are 70 million diabetics in India. There's a disease called diabetic retinopathy that is very common among diabetics, and there literally aren't enough ophthalmologists in India to be able to look at the images and issue diagnoses. And then when you look at things that may not be able to do at all, you look what's happened over time, just in the last decade. A decade ago, it was impossible for a computer to distinguish between a cat and a dog, something any 2-year-old can do with almost 100% accuracy. As you move through time, now a few years ago, all of a sudden, deep learning algorithms by Microsoft and Google and others were able to outperform trained radiologists in diagnosing disease in tissue images. So I like to give a couple quick examples. The cat versus dog is something very, very well understood. You can understand how that could be possibly confusing. There's a lot of similarities. They have 4 legs, they have a nose and ears. But how about just distinguishing between a dog and a muffin? That seems like it'd be pretty trivial. Obviously, dogs have hair and ears and nose and eyes and legs. Muffins are round. They may be dome-shaped. They may be in a wrapper. But once you get into the edge cases, in looking at real-world data, you realize how messy the world actually is. And this is obviously a fun, silly example, but in any domain you want to look at, you're going to find cases like this, where no matter how smart you are, no matter how much you think you can write algorithms to distinguish between 2 seemingly, absurdly different objects, you're going to find situations like this. So obviously, machine learning, as we just heard about in the last talk, is being applied in lots of different domains. Self-driving cars is a very obvious one. Communication, we're now starting to be able to translate in real time. So the Star Trek Universal Translator is coming soon. And of course, there have been some great headlines about playing games. Google had a program a couple of years ago through DeepMind called Alphago that beat the top world players. And more recently, there's been a new version called Alphago Zero. The original Alphago was trained by feeding in lots and lots of game examples from top humans and then letting it start to work on itself. Alphago Zero started from base principles. The program was taught what the rules of the game were, and then it just played against itself. And once Alphago Zero was ready, starting with training, in 3 days of training, it beat the version of Alphago that beat the world champion Lee Sedol. In 21 days of training, it beat the version of Alphago that had advanced a year and beat 60 top champions, including KG, in 3 straight games. After 40 days, it beat the best version of Alphago, what we now call Alphago Master, this kind of hand-coded neural network. And now it is continuing to learn from that. So these new systems are being able to grow exponentially now on their own. So Google has a series of pre-trained models that are accessible to anybody. There are, obviously vision, translation, natural language development. I'll have links to these on my last slide, so if you want to hold off, you can get links to these at the very, very end. So I want to show off one on vision as a lead-in to what I'm going to talk about with AutoML. So the Vision API takes the pixels of an image, and it then gives you back information about that image. It will detect objects, it will label, it will give you the OCR, the text within the image. It'll do logo detection, so if you're doing IP protection, for instance, you can find these things and then identify them around the web. It will also tell you whether an image is likely to be considered adult content. So if you don't want things showing up on your website unexpectedly, you can filter this so that you're keeping it safe for the family. So this is an example. I was in Mexico City last week giving a similar talk at an Apogee conference. And this is in a stairwell in the Mexico City office. I was curious how the Vision API would do with OCR on this image. So I took a picture, I fed it into the model, which you can do. You can just drag and drop a photo onto a page. I'll give you the link at the end. So you notice the yellow lines around each piece of text. It identified all that text, and I was really curious how it would do on the angled text, and it did it perfectly. It breaks it down into paragraphs, and which then you can then use, obviously, to have metadata to inform what is in the image. Landmark detection, obviously a very, very well-known object. There's a simple REST API. You upload the image, you tell it what portions of the metadata you want back, and it will reply. So in this case, it has correctly identified this object as the Eiffel Tower. That MID, I don't know if that text is too visible or not, but the MID is the ID into Google's knowledge graph. So any object that is identified as the Eiffel Tower will produce the same MID in this case, so you can then go explore additional information about that. It indicates the confidence, so in this case it's 90% confident that this is the Eiffel Tower. It gives a bounding box for the area of the image that it used to identify this particular thing. And in this case, because it's a landmark, it also shows the location in latitude and longitude. It can do other things that aren't quite as well known. So this is obviously a car. When you run this through, it says that, oh, this is an interesting car. It happens to be in a museum. It tells you where it is, and again, it shows you where you can find additional information about that. It identifies this car. It's a Ford Anglia. Well, I wouldn't have been able to tell you that, but I'm glad that the Vision API knew. But what's interesting about this car is that this was a car used in the Harry Potter movies. So it is able to identify that specific car, where it is in the context, to give you more information about that particular object. It will also show you where you can find more information about this. So it'll tell you where you can find identical matching images on the web or partial images, so you can see who else is using this image out on the web and possibly find out additional information. Again, this is a very simple REST API. Here's a little code snippet in Node. You just set up which pieces of metadata you want back, you submit the image, and then you get those particular objects. So let's do a quick demo on that. So again, this is a page. It's cloud.google.com/vision. You can go there. Anybody can try this with any image that you like. I have a couple images that I'm going to try out here. I'm just going to drag that in there. And again, it's an image of the Eiffel Tower. But interestingly, this is not the actual Eiffel Tower, but it is the Eiffel Tower at the Paris Hotel in Las Vegas. And the Vision API was able to distinguish that. So as we go through the information you can collect, you attach, there are labels, so you can categorize the image. So in this case, it's a landmark, there's sky, it's a tower, etc. From the web, there are links to the Eiffel Tower in Paris, Las Vegas. It has certain properties of colors and shapes. And it says that this is likely not to be an unsafe image. And then the actual JSON that you can then pull into your program to then collect and store, process the information any way that you like. So let's go back here. So that's great as long as the images you're trying to recognize are similar to images that can be found on the web. It's a general purpose model that's very good at identifying general purpose types of subjects. But let's say I have some domain specific information that I'm trying to use. So let's say that I'm a route planner for an airline or possibly a logistics company, and I need to be able to predict the weather. And I have heard that I can do that a little bit by looking at clouds. So I want to be able to predict the weather based on images that are collected locally at any given point for the event that I'm trying to do. There are 10 plus types of clouds that all indicate different types of weather. So we want to know if we could use the cloud to analyze clouds. And first we can try the standard vision API, and it will tell us that yes, indeed, that is a cloud. But it will not tell us anything about the type of cloud. So this is where we're able to apply AutoML. So traditionally, there have been, you could use a pre-trained model like the Vision API, or you had to go all the way to the far end and build your own neural network, your own machine learning model to be able to work with the specific trained data that you wanted to use. AutoML puts in the middle where it's a transfer learning process. It builds on the pre-trained model, but then takes your additional data, your additional tagged data, and applies that and builds a neural network that can distinguish those objects. So I'm going to jump into a demo now real quick and show you how this looks for this model we built to train clouds. And then I'm going to go further then into a little more detail on what's going on behind the scenes. So that is distinctly not readable. Is that better? Can you see that at all, or more? Let's try it there so I don't end up with too little things to see. So currently AutoML is in early access, so there are 200 customers using this. It's not generally available yet, but I hope we're going to hear more about additional accessibility coming up at Next in July. I don't have anything specific that I know, but I'm hoping we're going to hear more at Next. So in this case, this is a completely web-based protocol. You come in and you identify the images that you want to use. In our case, we went out and asked the people in our developer relations group to send us any images of clouds that they had. We collected about 1,500 images, and we then needed to get them tagged. You'll notice that as I mouse over each of these, it tells us what type of cloud that is. It's cirro, the last one here is cirrostratus. Now, we needed someone skilled to be able to do this. None of us are really experts in clouds. So we started looking around how we could find maybe a meteorologist or something to help us tag these images. Well, it turns out that Google has a meteorologist on staff. And when I first heard that, I kind of did one of these, eye roll and things, until I figured out that the reason we have a meteorologist is because of Project Loon. So this person is an expert in high-level cloud and high-level wind motion, So he built the model to help maintain those balloons over particular areas to provide internet coverage after disasters. But he was very generous to go through and tag all of our images for us. So in this case, you need to first define the tags that you want to use. So in this case, we have altocumulus, cirrocumulus, cirrostratus, cirrus, et cetera, et cetera. And then you go through and tag the images. And if you don't have the ability to do that yourself, you can actually use a human labeling service that we provide to be able to get that data, tagged. So we were able to get the data tagged, and as I said, you can see here all the different images. And you can look a little further and say, what do cumulonimbus looks like, and see all the different images. So once you have that data, then you're going to train the model. The way AutoML works today, there are two different models, two different model styles you can use. What we call the base model is free. It's a very quick. It builds a relatively small network to distinguish the images. Or you can do a more advanced model that takes several hours. You have additional data requirements for that. In the base model, you need as few as 10 images per tag in order to get some level of prediction. More data yields higher confidence in those predictions. So in this case, the model we built was actually is the advanced model. And we can now go in and learn something about this. So there are precision and recall curves that is done. So we automatically, in training the model, we withhold about 20% of the data for doing testing. And in this case, we see that the false positive rate and false negative rate is fairly good. We can expect to get reasonable predictions in this case. So 84% precision and 70% recall. And it also gives us the confusion matrix. So we can see where we're likely to have problems and where we may want to collect more data in order to increase the confidence in our predictions. So let's go ahead and do some predictions. I can do that from here in the web-based AI, but I'm going to go, we built a small application in Firebase that runs on the web or runs on your phone, so I'm going to go ahead and do it in that. So I'm going to upload a cloud photo. And this may take a few seconds to fire up. Okay, good, it did it right away. So it says this is a cumulus cloud with 96% confidence. And you can, in your case, you're trying to predict the weather. It says this is probably okay for your event. These are typical on warm, sunny days, and life is good. But if I get from another location, I get another image, and it runs the prediction on this. And this one is a cumulonimbus that it says it has lower confidence in this case. We went to the confusion matrix, we could see why. In this case, it says, uh-oh, this is likely to cause thunderstorms. So you may want to go order that tent quickly. So that is the demo. So let me go back to the slides and tell you kind of what's going on behind the scenes here. So the intent of this type of system is to be able to allow researchers, companies, people to add their own specific domain information on top of the pre-trained models. So examples in manufacturing, examples in retail, to be able to identify styles of clothing, for instance, to make predictions of what someone else may want to purchase next. Disney is using this to help customers be able to find additional video resources and additional products related to a particular character that they like. So if their daughter is into Ariel, they can quickly recommend things that the person can do to help spend more money with Disney. So this is an entirely database system. You need to know absolutely nothing about machine learning, neural networks, anything else in order to use this. You upload the tag data. It runs a series of model creations and trains and tests that data to see which network architecture is going to yield the best results, and then makes that available for you to do predictions. So there are really three key concepts going on here for AutoML. The first is it has to find the correct neural network architecture. And traditionally, neural networks, including all the big ones at Google have been, painstakingly hand-built and refined over years. There are not a lot of people with the skills to build those type of networks and do the ongoing training and refinement. This is a very challenging thing to do. You also then, it uses transfer learning. So we're using, let's say, of a 50-layer network for doing vision identification. Perhaps at layer 40, it jumps in and now has identified multiple classes of objects. You can then insert your portion of this trained model based on your domain-specific information to allow it to identify those objects along with the broader information. And then it has to automatically find the correct hyperparameters in order to tune that to yield the best results. If you want to learn more about this, you can go to the Vizier paper. There are links online. Anybody afterwards wants to come see me, I'm happy to give specific links. So this is all our very basic stuff for the next couple of slides, just kind of reinforcing how these things work. Neural network to distinguish between a cat and a dog. Someone would build multiple layers. The neurons would be, the neurons that were successful would be reinforced through the hyperparameter tuning, and at the end of that, you get an output of a cat or a dog. These neural networks are built up. Each layer does some number of different things. So the very first levels may just distinguish edges and colors. Then it's going to identify features and then groups of features until it finally can distinguish a Labrador retriever from a tiger cat. So this is what the Doodlenet model for vision looked like in 2015, I believe. This is the beginning of inception, and it was state-of-the-art vision recognition algorithm at the time, 39 layers deep. In order to tune, not just design that network, but in order to design the neural network and then tune those parameters, obviously is lots and lots of work. There's a tool, this is a grid visualization tool for understanding that process. And I'm a very visual person, so I like using this. So I'm going to go drop into a demo on this. You can try this yourself at playground.tensorflow.org. So this is kind of a cool tool. So can you see that a little bit? So this has different data sets that you can try to train a model on. This multicolor spiral is kind of interesting. I think it's the most difficult one they have in this example. You see there are red and orange dots. The orange dots are -1 and the blue dots are 1. And we're trying to distinguish between those. So I can start out with this example model. I'm going to use a rectified linear unit activation layer, and I'm going to try this using the default suggested network. And it's going to run through you see the steps counting up in the upper left. And as it learns, it's trying to show you what's going on here with the colors here. So the blue is it's starting to refine this. The blue is the prediction area that it's trying to match to the data. And you see this is not doing very, very well. It's doing quite poorly, as a matter of fact. So this example is not a good thing. So let's go ahead and try a hyperbolic function on this using the same network, and let's see how it does. So I'm showing this because there are lots of ways to design a neural network to achieve the goals that you want. Some are going to be effective, some are going to be efficient. Finding the optimal spot for that is challenging. So this also doesn't look like it's doing too good. So let's go ahead and stop that. And because this is the data here we're trying to fit is circular. So let's go ahead and add sine function onto this and see how we do. And now I'm adding additional features at the first layer, and this is starting to look a little bit better. So now, I don't know if you can see the numbers, probably not. Yeah. So let me blow this up a little bit, see if it can still fit this here. There we go. So you see that underneath output up here, it has test loss and training loss. So right now it's about 5% test loss, and it's done a little over 1,000 different iterations trying to tune this. And it hasn't done too bad, but it still doesn't really look like the data we're trying to fit. So let's add a couple more neurons here in the second layer and try it again. And you see now it's starting to get to results much faster. This network is now better designed to identify the traits in this particular data set. So now we're down to 1.5% test loss and under 1% in the training loss in this. But it still looks a little bit pained there. So let's try adding a layer and see what that does. So here's going to, you notice there was some jitter there. It had a little trouble passing through some domain set. There it is, it's jittering again. So it's a little bit stuck there, okay? But we're like 3% left, so we've made a more complex network that isn't as good as what we had before. And this again is a real world case that you see when you're defining these types of neural networks by hand. So let's go back down to where we were. I'm going to add one more neuron here, see how we do. And let's see, so I'm going to go run that out to 1,000 again. And here now, I see the spiral structure that I'm expecting to see. It's a good fit for this set of two-dimensional data. So I'm at 300 now. I'm already down to 1% test loss and under 1% on the training loss. So this now looks like a pretty good network for distinguishing the features I want within this data set. I'll let it run out to 1,000 and see where we end up here. And it looks pretty stable, so it's gotten to as good as it's going to get. So we're at 0.5% on the training loss and 1% on the test loss. So again, I wanted to show that to kind of demonstrate visually that more complex networks aren't necessarily better. You want to find the sweet spot. And that sweet spot can be, depending on what you want to look for. Do you want incredibly high precision? Do you want efficiency? There's some combination of those values that produce the function that you want. So let's go back here. So this evolutionary approach to identifying machine learning models is what AutoML does. This is showing an extreme example it starts out with a very small and effectively random neural network. And then it tries other examples of architectures, additional layers, additional nodes at a given layer, and it keeps trying. The ones that produce good results, it continues to refine those, and it ignores the ones, it drops the ones that weren't producing good results. So in this particular graph, the gray nodes have all been rejected, and the blue nodes are still actively being tried. So this is some number of thousands of iterations that's gone through to pick out a particular model. And you can see what that model looks like at various points along the way. And this is all in published paper as well, so you're welcome to go explore these all in greater detail. What's interesting is this methodology of evolutionary neural networks is already achieving better results than many of those hand-tuned, hand-refined models that have been built by researchers over time. So very quickly we saw that even a relatively small model in AutoML was beating Inception of a couple of years ago. And as we train it further, it is producing better results than the best hand-trained models today. And what's also interesting is that it's producing neural networks that humans really haven't conceived. Humans have biases, and we have tools we learn to apply. the machine learning doesn't really care. It's going to try things randomly and see what works, and then go off and explore that further. So the model on the left was a recurrent neural network designed by humans, and the one on the right was designed by AutoML. And it had higher performance than the hand-trained model. So you also then get into the tuning. You saw the tuning of the hyperparameters as in the playground TensorFlow, as the colors were morphing. That's the hyperparameters being tuned to show the results with that particular network. The space to do that, the amount of computation necessary to do that, if you're applying it on random networks, you're going to see that basically you're going to use all compute cycles for the rest of humanity if you don't do that in some type of intelligent way. So even in a simple case of 4 parameters with 3, 10, and 5, you have a 12-hour training time to do training data and test for each one of those examples. You end up with basically an entire year of compute to fully map out all of the potential space. And our human brains are good at looking at 2- and 3-dimensional objects. When you go deeper than that, we lose the ability to visualize. So this is a nice example using 3-dimensional data. What we want to avoid is finding these local maximums that look like the potentially best solution. We have to explore lots of space and see where we're going to reach the highest possible maximum. So in this case, we don't want to find all these waves on the left. We want to find the best result up high. And so what AutoML is doing is it is running about 20,000 different network architectures in that advanced model. And it figures out for your particular data set which ones are yielding better results. And in this example, I see that we had one here with a moderate learning rate and a moderate number of layers that had a data fit of 97%. By slowing or speeding the learning rate, or by adding additional layers, it doesn't get any better than that. So AutoML is designed to be able to identify those domain maximums and be able to get there quickly, and then be able to train that model to do, hopefully, even better than you could do by writing the model yourself, without all that years of expertise necessary to do it on your own. So I have lots more stuff here on some of the other pre-trained models, but this talk was intended to be primarily about AutoML, and we only have 5 minutes left for questions, so I think I will leave it there. This is the links to the pages where you can go try out these yourself. You can upload images, you can upload videos, you can type in text to translate, you can send an audio file and get the text back. They're all very handy things. And today, AutoML is only available within the vision domain, and there have been no announcements about anything more than that, but I think it's reasonable to assume that Google would be interested in making AutoML available within other domains along these lines. So with that, I will take any questions that you might have.